Okay, today we're going to talk a little bit about weak acid equilibria. So we've talked a lot about equilibrium, and we know that dynamic equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction. So if we're looking at this particular reaction, then we have HA, which is a binary monoprotic acid. So remember that monoprotic means that it has one proton, monoprotic to donate, right? So our Bronsted-Lowry definition is that an acid is a proton donor. So in this case, my HA is donating my hydrogen to my water, which forms hydronium. And then what's left over from my acid, or my conjugate base here, is just the anion, whatever that general anion would be. So if I was thinking about this in terms of equilibrium, then we could talk about the equilibrium constant. In this case, the equilibrium constant has a subscript of A, when we're talking about an acid that's dissociating in water, or that is showing its acidic behavior in water by dissociating. So that's a Ka value. Ka is going to be important as we move forward because we're going to use that value to give us information about the strength of our acid. So here's our Ka. The expression for this is going to be the same as we've seen. So it's going to be the concentration of our products, our hydronium and our anion, over our concentration of our reactants, which again is just our generalized binary acid here. So I didn't include the water, you'll notice, because it's a pure substance, it's a pure liquid, so it's not going to be included in our overall Ka expression. Now, if we were thinking about this in terms of just generalized information, if we thought about an ice box for this guy, or an ice table, remember thinking about our equilibrium concentrations, let's just say initially we have some concentration of our HA, and we lose some amount of it, some molar quantity of it, so at equilibrium we'd have HA as a concentration minus X. We're going to ignore our water, so I'm just going to kind of cross out that particular part of our ice box or our ice table. And then let's assume that we don't have any of either of our products. The molar change here is going to be plus X. It's all 1 to 1 to 1 to 1. So if we plug this into our expression, then we'd have our Ka is equal to X times X. There's our hydronium times our anion. And then that's going to be divided by our quantity of the acid minus X. Now, one important feature for this to remember is that if we compare the magnitude of our Ka value to our concentration of our acid, if there's more than 1,000 times difference, so more than 3 orders of magnitude difference, then we know that we can disregard the X here with respect to the concentration of our acid, right? Because in terms of our values, it's just going to round out, right? So we would just, significant figures wise, it would round out. All right, and if it doesn't, then we'd have to use the quadratic equation, which is fine. We're snappy with that. So let's look at an example. So here's our example with our hydrogen cyanide. Hydrogen cyanide is a weak acid. When it reacts with water, it forms hydronium and the cyanide ion. So if I have a specific concentration of my hydrogen cyanide, I have this Ka value. What does this Ka value tell you about this equilibrium? Does it favor the reactants or does it favor the products? And hopefully you're thinking to yourself, well, it's a small number. It's a number significantly less than 1. So that means that it must have a larger denominator than a numerator, which means that it must favor the reactants. If it favors the reactants, then what does that mean about this acid? Is it a strong acid or a weak acid? And hopefully you're thinking to yourself, well, if it favors the reactants, that means I have a greater concentration of hydrogen cyanide at equilibrium, and therefore it must be a weaker acid. And so the magnitude of this Ka value is going to give you information about the strength of this acid, or the strength of the base once we get there. So let's make our ice table, or our ice box. We start off with 0.45 molar of my hydrogen cyanide. I'm going to ignore my water. It doesn't say that we start off with anything products-wise, so we're going to leave those alone. Again, it's all 1 to 1 to 1 to 1, so it's a monoprotic acid. So we're losing the molar quantity of X here. We're gaining molar quantities of X, which gives us this for concentration and this for concentration for our products. Now we know that the expression for our Ka, so here's our Ka, which has this teeny tiny magnitude. This is going to be equal to the concentration of our products, let's call that X squared, over our reactants. And I'm dropping my units there just for ease of calculation. And if I look at this problem and I compare the magnitudes of my Ka value to my concentration, there's greater than an order of 3 orders of magnitude difference. So I'm going to disregard this X. Because if I was thinking about this in terms of significant figures, then it would just round out. So I don't have to worry about it. So I'm going to disregard that X, which makes my math a little friendlier. So now I'm going to have an X squared that's equal to this 0.45 times this value here, which gives me 2.2 times 10 to the negative 10th. And hopefully you're checking my math and doing the math along with me at home. When I take the square root then to get rid of that exponent, we know that when we take the square root like that, it gives us two values, a positive and a negative value. So I end up with plus or minus 1.48 times 10 to the negative 5th. And you'll see that I've kind of grown some significant figures there. We'll round at the end. Now we know that this value X represents actual physical things. In this case, it represents the concentrations of my products at equilibrium. So we know that this concentration can't be negative. So we really only have one answer that's possible within physical parameters, and that's my plus 1.48 times 10 to the negative 5th, and this is equal to my hydronium ion concentration. Now that answers the first question here, which is what will the concentration of hydronium be at equilibrium? Well, I figured that out. It's that 1.48 times 10 to the negative 5th. But the second part of the problem is, what is the pH? So if you recall, pH is equal to the negative log of the hydronium ion concentration, or the hydrogen ion concentration. Pardon my messy bracket there. So if I plug this in, here's my pH is equal to the negative log of my 1.48 times 10 to the negative 5th. And when I plug that in, then I end up with a pH of 4.82. Now, if we're thinking about significant figures, which we always are because we're scientists and we value precision, then remember that for logarithmic quantities, when we're doing logarithmic operations, that two significant figures are represented by the number of decimal places that you have. So if I have 2 decimal places here, that means I have 2 significant figures, which is what I'm looking for. So that's my final answer. That answers both questions. First, that my hydronium ion concentration is 1.5 times 10 to the negative 5th molar, right? So if we were actually thinking sig figs here, final answer, 1.5 times 10 to the negative 5th molar, and my pH of my solution at equilibrium is going to be 4.82. Now, if we think about this in terms of our pH scale, we know that that's on the acidic side, but not crazy. If we think about some comparisons to some of the things that we've talked about, this is kind of in the range of sort of coffee kind of acidity, depending on the way that you like to drink it. So that's it for weak acids and equilibrium, and a little bit of practice with an ice table there. And we'll pick up with some practice with bases here soon.